Okay, so today's lecture actually did not exist like a year ago, and we added it because people were saying they wanted to see more complicated exploits than the ones we showed you last week. So today, all we're going to be doing is looking at some pretty hard exploits. Some of them are going to look really similar to the exploits you're doing for Project 1. So think of today as like the Project 1 guide lecture. Not really any new content today. It's mostly just things that you've already seen, but harder and closer to what you'll see on Project 1. So that's the plan for today. We're not doing any new content necessarily. It's mostly stuff you've seen before. Maybe there's a little bit of new content, but mostly it's taking stuff we've seen before, applying it in harder problems, and hopefully giving you a better time on Project 1. So that's why this lecture exists. We made it in spring. Hopefully there are no more bugs. I think we caught a few in spring, but we will cross our fingers. Okay, that's the plan. Okay. Okay. So the first half of today will show you format string vulnerabilities, and this is one of the exploits that you'll be doing in Project 1, which is kind of why this exists. So this is a bit of a different flavor of memory safety vulnerability, and it requires being really familiar with how the printf function works. So one thing you might remember from 61C or any C programming class is that the printf function, it takes in a variable number of arguments. You can pass in multiple arguments and printf will accept it. So how does it know how many arguments it receives? Well, somehow there has to be this mapping between the format string that you provide and the arguments that you pass in. So for example, this is a printf call that you could do. You could say 1%s costs %d. And what you're doing is in that very first argument is the format string you care about. And in that format string, you can add these special percent followed by character symbols. And what this %s says is say, go to the corresponding argument. And in this case, this is the first % argument that I find. So I match it up with the next argument, which is fruit. And then this %d, that's the second % argument that I find. So I match it up with the second argument, which here is price. Okay. So if you've seen printfs before, this is generally how they work. You can pass in a variable number of arguments. And the hope is that the number of arguments that you pass in after that initial format string matches the number of % formatters that you have. And then what does printf do? Printf takes the variable fruit, reads it as a string, and then replaces the %s with the value of fruit. And then it takes the variable price, reads it as an integer, that's what the D stands for, and then takes that integer and substitutes the %d with the integer. And if you have a lot more % formatters, then it does one match per % formatter. Okay, but we're a security class, so we're not here to do what's expected and give printf the right number of arguments to match the format string that we provide in the first argument. We're here to do funny stuff. So let's try to give printf functions that are mismatched. So what does that look like? Well, here's an example of a nice version of printf where we pass in the right number of arguments. How do I know that? Because I look at the first argument that I passed in, that special one. That's the % formatter. And in the % formatter, it's just a string, but in that string, you can have special % formatters that get matched to future arguments. So I just have one % formatter here. It's the %d. So printf says %d, you pair up with the next argument, 1, 2, 3. So I'll take the 1, 2, 3, plug it into the D, and that's what gets printed out. Now, what does that look like on the stack? So just like in all the previous lectures, we can draw our stack diagram. And in our stack diagram, here are like the highlights. So we declare the secret local variable, it's right there. And then we call printf. So we're still calling function. Function hasn't returned yet. So we're still going to leave the stack frame for function. But while we're calling function, we're now going to go call printf. So we're going to create a new stack frame for printf. And what does that new stack frame contain? Well, first, when I call printf, I pass in the arguments. So I pass in the arguments in reverse order. That's one of those C trivia rules that you just remember. So the first argument I pass in on the stack is the 1, 2, 3, because I'm going in backwards order. Then I pass in the %d. And if you remember your string syntax in C, remember that in C, strings are really references to strings or references to character arrays. So instead of passing in the actual characters %d new line, I'm passing in the address of wherever that string lives in memory. That's the argument that I pass in. Okay. And then eventually, now I'm ready to call printf. So I create this big old stack frame for printf. Now we don't know what the code of printf is, so we don't really care what's going on in there. but do know that the frame for printf does exist while we're doing these vulnerabilities. We just don't really care what's inside. What we care about is going to be this stuff up here. Okay, so that's me drawing the stack frame for the function that you see on the left. There are local variables. Then I called printf. So I put some arguments on the stack. And the only one that was kind of weird was the string argument, where we had to remember that strings are really references to character arrays in C. Okay, so, well, what do we do? Well, printf, in this case, the arguments are matched well, so nothing malicious is going to happen. So what does printf do? Printf takes the first argument. I'm going to start calling it the 0th argument because it's the format string. And then we'll say the first argument is the one after it. So I'm going to start 0 indexing just because I think it looks nicer, but this is not like common convention or anything. So I'm going to start calling this one the 0th argument because that's where the format string lives. That's the special string that you provide where any of your %ds or %s's will be replaced by one of the arguments. So printf, what does it do? It reads this string that I passed in as arg0, the very first thing that I passed in, and it starts scanning through and looking for %. And it sees, uh-oh, there's a %d right there. So what do? I go back on the stack and I find the next argument that hasn't been used up yet. What is that one? That's arg1. So now I know that arg1 is the argument that matches up with this %d. So I'll take that 1, 2, 3 on the stack, read it as an integer, plug it into the %d, and then go on my way printing the null byte and whatever else. So that's what printf does. Printf, it goes to the 0th argument in memory where it should find a string. It reads that string and prints it out character by character. And anytime it sees one of those special % formatters, like the %d, it goes on the stack to find the matching argument and plugs it into the %d. Okay, that's what it looks like when things work well. So if things work well, we get the 1, 2, 3. Now let's try to be a security class and take away one of the arguments. Now there's a mismatch. Printf should, if I were to call printf correctly, there really should be another argument after the 0th one. Because in my 0th argument, the format string, I put a %d. So I should really have given printf another argument here to say, here's what you should plug into the %d. But I've decided not to do that. So what happens now? Well, the only difference on the stack diagram is that there's one fewer argument to push. Secret variable is still there. The stack frames are still the same. The only difference is I wiped out this argument. So this argument no longer gets pushed on the stack. So it's gone. The rest of the stack looks just the same. Okay. And just like before, we think about what does printf do? We can't see the code for printf, but we know what it's doing. What it's doing is it goes to the 0th argument, that special format string on the stack that was passed in, and it starts reading character by character. And anytime it sees that special % symbol, it's like, uh-oh, time to go substitute in something from the stack. So what does it do? It looks at the %d and it says, all right, that's a % formatter. That means that the user has passed in another argument that's going to match up with my %d. Where's the argument going to be found? On the stack. So to the stack we go. And where is printf going to look for the argument? It's going to look directly above the format string argument, arg0. So if we look at the previous example, that %d, where did it look? It looked 4 bytes above arg0. Cough, okay. And then what happens here? We look 4 bytes above arg0. And what do we find? We don't find the argument because the user didn't specify one, but instead we find the secret number that was in the code. And now the secret number gets associated with the %d. So what will this print out? It'll print out the 42. Our secret has been leaked. And that's because we passed in the wrong number of arguments. This is like our hello world of printf vulnerabilities. We mismatched the number of arguments. So when the printf function went to the stack to look for arguments, instead of finding the argument that was pushed on the stack, it found something else. In this case, some secret variable that got printed out when it shouldn't have. Okay, so that's unexpected behavior. Now let's try to use it to do something bad. There's a piece of code that you might write, I might write. It looks more realistic than the one we had before. So we've got some character array like we always do. And we try to read it safely, right? So this is memory safe version of reading where we say, don't read past 64 characters, right inside bounds. And I know that this is safe because I've looked up the fgetS function and it's doing what I expect. So it's not going to let me write past the end of buff. Okay, I'm happy with that. And then what do? I call printf on whatever the user supplies. Okay, is that bad? Well, that might be bad. Imagine if the user supplies something malicious where the arguments are not matched. So then we have a problem. So these are called format string vulnerabilities. It's a big category of vulnerabilities, and you get to suffer through one in project one. So have fun with that. Okay. What's the problem here? The problem is that we've called printf with just a single argument, the first one, that special 0 argument, or the 0th argument, the format string. That argument is special. The 0th argument, the very first one that you pass into printf, that argument is special because printf uses that argument, reads it, and anytime it sees a %, it goes on the stack to find an argument to pair up with the %. And what have I just done in this code? I've given the attacker total control of whatever they put in that printf. So I don't know, maybe when you write C, sometimes you're like, I want to print something. So I just call printf on that thing. But as we can see here, that could lead to really bad things if you're not careful with printf. So what could the attacker specify? Well, let's come up with some examples that use a bunch of %. So here's something that the attacker could specify. If they specify some string that has the %d inside, what's printf going to do? It's going to read this string, the 0th argument, in a special way. It's going to go through character by character. The 1, print the 1. The 0, print the 0, print the 0. Then it sees the %d, and it's like, uh-oh, %d. I need to go on the stack, take the next thing on the stack, read it as an integer, and print it out. Okay, so it's going to print something on the stack that was not intended to be printed, because there should have been another argument here, but there wasn't. So instead of getting the argument that should have been there, printf goes in the stack, grabs who knows what, prints it out as an integer. What about %s? Kind of the same style. We read the 100, print it out, then we see the %s, and we're like, time to go to the stack and get a string. Now, what does a string look like in C? Remember, in C, strings are references to character arrays or pointers to character arrays. So we go on the stack, we take the next thing on the stack. It's not a string, it's a reference to a string, or at least the %s says so. So what are we going to do? We're going to go on the stack, take the next thing. What is printf expecting? It's expecting that you put a string here, but there's no actual string there. So we go on the stack, we take the next thing. We expect it to be a pointer to a string, but we don't find it. So who knows what we find? But whatever we find there, we pretend like it's a pointer to a string. We go to that address and then print out whatever is there as a string. And what's a string in C? It's a character array ending with a null byte. So wherever we go in memory, we start printing out characters until we see a null byte. So that's just the behavior of strings in C in a format string context. So in C, just to read it one more time, because it's kind of confusing. In C, you don't have the actual string stored on the stack. You have pointers to the string wherever it is in memory. And then you have to dereference that, go to that location, and then print out characters until a null pops up. Okay. There was a question about the space. So I guess this was just done to have like funny words or whatever. The space, I don't think we're going to talk too much about it. I don't know off the top of my head if the space in between those two stops the printf, but I guess we can assume there's no spaces. I think they just wanted to put funny words in the slide. Okay, that's a good question though, from Zoom. Okay, and then here's another one where we say %x, 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 %x. So if we do this, what is printf expecting? Printf expects that there were a lot more arguments placed in this printf function that were all pushed on the stack on top of the 0th argument. So what's printf going to do? For every %x that it sees, it's going to go on the stack, grab the next thing that hasn't been used yet, treat it like an argument, print it out in hexadecimal. And it's going to print all sorts of stuff on the stack that probably were not intended to be printed. Okay, so these are bad things that the attacker could do with the format string vulnerability, because we've given the attacker the option to pass in anything they want into that special 0th argument where the % matter. And so if the attacker puts in % and we don't match them up with more arguments, then now unintended things start to happen with values on the stack. Because printf goes on the stack, takes the next value, thinks it's an argument, but it's not actually an argument. Okay. Let's try using this to do some bad things. So there's another little piece of code starting to get a bit more complicated, but this one is kind of the same pattern as before. So we had some character array down here, and we're going to call printf on it. So we're going to let the attacker put whatever they want here, and then we're going to call printf on it. Okay. Just like before, the fgetS is here to let the attacker write into buff. That's safe, so they can't use the fgetS to write over, but maybe they can do bad things with the printf. So, and again, strings are kind of weird. They do take a bit of time to wrap your head around. So for example, notice here that what I'm declaring is not a character array. I'm declaring a reference to character array. So that's why the secret string is down here. So in case you're wondering why the secret string is stored down here, it's because I declared it as a char star, which is a character array for a reference to a character array. If I wanted the actual string pancake on the stack, I would have had to say char bracket bracket to get the array. But that's like C minutia, so don't worry too much about it. Just know that this is the picture corresponding to this function in C. Okay, so there it is again. Now let's pretend we're the attacker and we've inputted %d%s. So now we're calling printf %d%s. This is mismatched because that 0th argument, that critical argument where all the percents matter, it's got 2% formatters. So printf is expecting that you passed in 2 more arguments to match up, but you didn't. Uh-oh. So now printf is going to take that first %d. Well, let's start walking through. So printf is going to say, well, where do I find the arguments? So what I'm going to do in this lecture, you don't have to do this, is I'm going to start using this column over here, limited space that I have, to start labeling what printf thinks the arguments are located. So for example, printf thinks, and it might not be right if the arguments are mismatched, but printf thinks that's arg0. That's the place where I passed in a reference to the magical format string with the percents, the critical 0th argument. And then the thing above it, that's where printf would, that's where the second argument would go. So if printf had %d%s comma something else, that something else would go here where arg1 is labeled. And then if we said printf %d%s comma something else, then arg2 is where that something else would go. So this is just me keeping track of where printf thinks all the arguments are located, even if there are no actual arguments. Question? Yeah, there's a question of what if you spam so many % signs you run out of space on the stack? You'll probably run into some operating system error, because what we don't show is that somewhere really high up in the stack, you start to enter like operating system space or kernel space. So that's like an operating systems class thing. It'll probably crash and yell at you. So I don't know, maybe we'll try it someday. Okay, good question. Okay, so this is just me writing down, okay, if I'm printf and I'm imagining where printf thinks the arguments are, printf thinks that this is the argument after the % formatters, and then printf thinks this is the argument after the % formatters. Is it actually? Probably not, because we have the mismatched arguments, but that's what printf is thinking. So that's a note that I wrote to myself. All right, so here we go, we're printf and off we go. So we start with the %d and we're like, all right, time to go on the stack, take the next thing, substitute it into the %d. So on the stack we go, and we take the first thing on the stack, which the printf thinks is the next argument, and we shove it into the %d. And that thing on the stack, that secret number, it's 42. So 42 shows up. All right. Then we keep going. Printf sees the %s, and it's like, that's another % formatter. I'm going to go on the stack, take the next argument that was pushed on the stack. Now, nothing was actually pushed. Printf thinks that something was pushed. So we go on the stack, take that next thing, and now it's %s. So what does printf do when it sees %s? It says this next thing, you probably supplied a string because you asked for %s. And if it thinks you supplied a string, how does it print out a string? Remember, strings are not character arrays. They are references to character arrays. So this is an address of where the actual string is. So I'm going to have to go to that address, find the string, and then print out all the characters. So we print out P, A, N, C, A, K, E. And we see the null byte, and we stop printing. So that's the output that we get. We see the %d, go on the stack, get something, read it as an integer, see the %s, go on the stack, get the next thing, read it as a string. And to read something as a string, you go to that address and start printing characters until you see the null byte, which is just the byte 00. Okay, so 42 pancake is what you get if you pass in this input. All right, cool. Let's do another one. So I guess before we do another one, let's talk about, there's a really obscure formatter for format strings. So we know %d is for integers, %s is for strings. Now, what the heck is %n? This is one of those things that's like just really obscure C trivia. Unless you're like a security person, then this is, the stuff of your nightmares. So what the heck does %n do? %n, just like all the other printf formatters, it goes on the stack and finds the next argument. So %d goes on the stack, finds the next argument. %n also goes on the stack and finds the next argument. Now, it's unlike %d. What does %d do? It goes on the stack, finds the argument, reads it like an integer. What does %n do? It goes on the stack, finds the next thing, and reads it like an address. So it's going to go to that address. And then what's it going to do? It's going to write to that address. And what's it going to write? It's going to write the number of bytes that printf has printed so far. I promise you we will break this down more. It's a really strange formatter. As far as I can tell, basically no one uses it anymore. I think the reason why, if I had to guess, is so when you printed stuff out in C, things would like output, the spacing of output would look nice, but just really weird, really obscure formatter. So here's an example. Again, what does printf do? It starts going character by character in that 0th argument. And it goes, okay, I'll print that out. T, E, M, I'll just print those out as characters. Okay. And then it sees that %D. So what does it do? It goes on the stack, finds the next argument. Since everything is matched up, it will find that 3, substitute the 3 into the D, print it out. And then it sees this %N and it's like, all right, time to go on the stack and get another argument. And what will it find? It will find the address of the variable val, because that's what I put on the stack, address of the variable val. And then what's %D going to do with this thing on the stack? It's going to go to that address. And if I go to this address, what do I expect to find? I find val. What do I find at the address of val? I better find val. And once I go to val, what do I write in val? Because %N does a write. So it goes through that address, doesn't print anything out. It goes to that address and writes the number of bytes I've printed so far. How many bytes have I printed so far? Let's count. I, T, E, M, space, 3, colon. 7 things in total. So I write the number 7 in the variable val. Mysterious. Let's do another one. I, T, E, M, space. Those get printed out just like normal because there's no %, nothing special happens. And then printf sees the %D and it's like, I got to go on the stack, grab the next thing, which happens to be the 987 if the stack is set up correctly, substitutes it into D, prints it out. The colon, prints it out. %N, time to go on the stack, get the next thing that I haven't used yet, which is going to be that address of val. I'm going to read it like an address and go to that address. If I go to that address, what do I find? Val. If I go to the address of val, what do I expect to find? Val. And I write the number of bytes printed so far. So just like before, I can count ITEM space 987 colon 9 things. So I write the number 9 into val this time. So as far as I can tell, like, I don't think this really matters, but as far as I can tell, this %N is used to somehow like align the spacing so that if you were trying to print this stuff, maybe you want to make it look all nice. So the characters all line up. That's my guess. But honestly, %N is so strange that I don't think I could tell you if there's a practical use for it anymore. It's so weird, but it's in there. So people can use it. You can use it if you'd like. Okay. Now, what happens if you do %N with mismatch arguments? That's where stuff gets interesting because now printf is using all sorts of weird things on the stack that it's not supposed to use. And not only is it reading and printing out stuff and dereferencing stuff, now it's writing stuff into memory too. So suddenly printf is not only reading stuff, it's writing stuff. That's really dangerous. So what does this one do? It's mismatched arguments. So we print out the 0, 0, 0, just like always. And then we see the %N and we're like, okay, %N, time to go on the stack, get the next thing on the stack. And normally it should be some argument if the stack were set up correctly, but it's not. It's who knows what's on the stack. We'll grab something on the stack. We'll treat it like an address. We'll go to that address. What are we going to find? I don't know. Depends on what's on the stack. We'll go on the stack, get that address, go to that address. I have no idea what's there. And I'm just going to shove the value 3 there. So suddenly this printf call, it's writing 3 to somewhere in memory that we didn't expect. Strange. Okay. So normally this would just be some trivia in some C class, but since we're a security class, this is like, it's like Christmas for us. We can use this and start going wild with all sorts of different vulnerabilities that use printf to write stuff in memory, thanks to this %N. But it is a really strange specifier. So stop me if you want to know anything about it. Okay. Sorry, I'll try to do a better job checking Zoom chat. The reason why it's writing 3 is because it printed out the 0, 0, 0. So in total, 3 bytes of output showed up. Then the %N hit, so it went and wrote the 3 somewhere. Good question. Right. So let's keep going. Now it's the same demo as before, but instead of writing %D, %S, now I'm going to write %D, %N. So just like before, the %D, what does it do? Well, it goes on the stack, finds the next unused argument, which happens to be this, and then prints it out as an integer. And you get 42. Same as before. That's what %D normally does. Then we go to the %N. Here's the interesting part. We go on the stack, take the next thing that has not been used yet. And how do I know what that is? Well, that's this, because I already used arg1. So I'm just keeping track for myself what on the stack hasn't been used yet. I already matched up arg1, the secret number, to the %d. So the next thing that I'm going to match up to the %n is the secret string, arg2. That's what I've labeled it. So what do I do with secret string? I read it like an address. %n always says, take the thing on the stack, read it like an address, go to that address. Okay, %n, I will go to that address. I'll follow the arrow, and here I find the string pancake, or the place in memory where the string pancake resides. And what do? I don't print this, I don't read it, I write something there. So I'm going to write the number of bytes printed so far. How do I know what's been printed so far? Well, I have this little output box that tells me I've printed the digit 4 and the digit 2. So I've printed 2 things so far. So I'm going to go to that address in memory. I'm going to shove the number 2 there. So no more pancake. Now you're 2 ache and then a null point. Okay. So the output is just 42, but now I've taken parts of memory that I was not intending to change. And suddenly that string pancake, somehow some of it got wiped out with the number 2 because of this %n. Okay. Mysterious function. Let's try to start using it for evil. So to use it for evil, I'm going to use this picture. And the difference here is that I've decided to put the buffer on the stack instead of the heap, or instead of static memory. So just like always, we can draw the stack diagram. And I promise you, the more you do project 1, the more you'll come to love and appreciate stack diagrams. Okay, and especially when they give you free points on exams, you'll love them. But anyway, let's go to the stack diagram. So I guess I'll draw it for you, or I'll attempt to. So usually when you call a function, the first thing that happens is we have to create that stack frame. And I've done this a bunch of times, so I've started to notice the pattern that every time I create a new stack frame, 2 things always start showing up, which is the RIP, that's the address of wherever the code's going to return to when it returns, and then the SFP, which is whatever value is going to go into that EBP register, the top of the stack pointer, whenever I'm done. So every function that I call, those 2 things show up first. This vulnerable function had no arguments, so I don't put them there. Now I can start writing the local variables. So the first local variable is buff. It's 16. So I'm going to use the rule that each row has 4. You don't have to use that. But using my rule that each row contains 4 bytes, buff is going to take up 16 bytes. All right, so that's buff. Then I have another local variable. And remember, I put the first local variable at the higher address, the second one at the lower address. That's just our convention in this class. That one is size 12, so it takes up 3 of these boxes. Okay, now we're going to call fgetS. So in theory, some fgetS frame is going to appear down here. Okay, and then fgetS is going to do its thing. The attacker is going to write some stuff into the buffer. Then fgetS is going to return. And what happens when fgetS returns? That stack frame, gone. Remember when you return from a function, we always have to restore everything back to where we found it. So when fgetS is done, it's like it left without a trace. So our stack is clean again, and there's no fgetS function. But do know that if I was drawing this entire stack diagram, technically, yeah, the fgetS stack frame appeared, but then the function returned. So it disappeared again. Now it's time to call printf. So I could have drawn the stack diagram halfway through fgetS, but I'm not concerned about fgetS. I'm concerned about that printf. So I'm going to draw the stack diagram halfway through that printf call. So what happens when I call printf? Arguments. I push the arguments first. So the first thing that I push is buffer. How do I push buffer on the stack? Well, I'm not going to push the entire 16 bytes on the stack. That's not how C works. When C looks at a string or a character array, it's actually passing the address of wherever those characters are. That's just a little C syntactic quirk. So that's the argument. That's the one and only argument. There's no more. So now I can write the RIP of printf, the SFP of printf. Those don't matter too much for our exploit, but just know that they're there. And then down here, we have that printf stack frame. And what's going on in that frame? Printf probably has some local variables, but I'm not concerned with them. I just care about those arguments and how they're taken off the stack. So this is good enough for my purposes. All right, let's make it look nice. I think that matches what we just did. Okay, so that's how I build the stack diagram. Okay, now, just like before, if I'm thinking like printf, we're in printf, so I'm gonna think like printf. What are the arguments that printf thinks is on the stack? how does printf know where to look for arguments? It looks starting here and starts looking up for all the arguments. So as printf, if I'm thinking like printf, I can leave a little note to myself saying, if I were printf and I was looking on the stack to find arguments to make friends or match with my percent formatters, here's where I'd find them. Now, this printf didn't actually pass in any arguments, but so none of these actually are arguments to printf except the 0th argument. But if printf wanted to find an argument, like it saw a %d and it wanted to go on the stack to find the buddy to match up with the %d, this is where I would find them. Okay. There was a question about how does printf keep track of which arguments have been used up and which ones haven't? I don't know. I didn't write printf. So somehow printf is probably keeping track of which arguments match with which. We don't know how because we don't care or know the source code of printf. But as we're like reasoning through, we can imagine that printf somehow knows. Okay. There was a question about, will arguments written on the stack always be pointers? Not necessarily. If you go back to one of the earlier slides, we pushed the number 42, I think, as an argument. And that wasn't a pointer. That was just the value 42. Okay. Those are all good questions, though. So here's me building the stack diagram. Here's me leaving a note for myself, reminding myself that this is what printf is thinking. And this is where printf thinks all the arguments are. All right. More Zoom questions. When would which be used? So I'm not going to go into in too much detail right now, but for today, integers are passed by value, and then strings or character arrays, we pass the address. Okay, good question though. All right, so this is just me labeling, and it just tells me if I were printf and I had 7% formatters in that 0th argument, this is where I'd find them. All right, so here we go. Now I'm not going to give you an exploit and tell you what it does. Now it's your turn. Now you're the attacker, and you have this strangely specific goal, but okay, it's for our lecture. So in this strangely specific challenge, you want to get the number 100 written into the address deadbeef. Why? I don't know. Maybe something bad happens if you do that, but that's our setting. You want to get the number 100 written to this particular address. That's your goal. All right. Now let's start designing the input. So, well, this is not like those classic buffer overflows from last time, where I can just be like, oh, okay, I start writing a buffer and I can just, go along my way, overwrite some stuff and hope something bad happens, because that's not really what's going on here. In fact, the fgeta stops me from writing outside a buffer. So I'm actually limited to writing inside a buffer. So I can't do my classic buffer overflows from last time where I start at buffer, write my way up and overwrite something interesting. I need to take advantage of the way that printf deals with arguments that don't match. So here we go. This is really tricky. To me, format string arguments or format string exploits and the thing you'll be doing in project 1, it's like juggling to me. There's like 3 different things that have to be true at the same time, and you have to somehow make them all true. And sometimes when you change one to make it satisfy or make it work, the other one breaks and you're like, oh, I got to fix this one. And you fix that one, 2 more break and you have to fix those. And somehow you have to make it so that all 3 work at the same time. And it's like beautiful and everything is lined up in harmony. But doing that is really tricky. So let's try to juggle those 3 different things. We saw printf had all these different things it was worrying about, like where the arguments are, where it's writing to, how many bytes have been printed. All those things have to be juggled. When you adjust one to make it right, you might break 2 other ones. So let's go through and think about what those things you're juggling are and how you make it so that all of them line up together in some beautiful way to get this 100 to deadbeef thing working. Okay. So here are 2 things that you have to juggle. One thing you have to juggle is where you're writing. So we know that if we want to write something into memory, a %n has to appear. That's the only strange % formatter that causes printf to do some writing. So at some point in this buffer input that I'm giving to the program, there's got to be a %n. Where is it yet? I don't know. That's part of my juggling. But I know that when the %n occurs, what does printf do? Printf reads byte by byte, character by character, and eventually it's going to see that %n and it's going to say %n, time to write something. At the moment that that happens, both of these things have to be true. Not one, not the other. You need to juggle, get them both right. So 2 things have to be true. First, that %n, how does it know where to write? It goes on the stack, takes the next thing, goes through that address and writes there. So whenever the %n occurs, printf is going to go on the stack, take the next thing, go to that address and write something. Whatever address it finds had better be this address because that's where I want to write stuff. So I have to juggle and make sure that the thing or the location that I'm writing is what printf receives when the percent n hits. So when the percent n hits, I go on the stack, and the next thing that I haven't used, it had better be deadbeef so that I can go to that address and write something. The second thing that has to be true at the same time, which is what makes printf vulnerabilities so tricky, is you also have to make sure that it writes the correct value. How does printf know what value to write? It checks the number of bytes you've outputted so far. So at the time the percent n has occurred, the number of bytes you've printed so far, it better be 100, because if it's 100, that's going to cause printf to write the number 100. So you simultaneously have to make sure that the number of bytes printed out is 100. And when printf goes on the stack to find that next argument, whether it's arg 4 or arg 5 or arg 7, whichever one it takes off next for the percent n, it better say deadbeef. So let's attempt to do some juggling. Okay, here's an exploit that might work. So let's take a look at it and try to understand how it was juggling things. So, that's my input. Well, the first question is, when I write this input into memory, what does it even look like? So let's try writing it in memory. This is what it looks like. And right, you start seeing these percents and these like deadbeef addresses, and it starts to get a little confusing. So we have to remember, what is this deadbeef thing? That's a 4-byte address. It's 4 bytes. It's the EF byte, the BE byte, the AD byte, the DE byte. And those show up in memory right here. It's 4 bytes long. There they are, right? What comes next? The percent character. How long is the percent character? It's 1 character. And then the 9, that's literal character 9. Why is that the case? Remember, what is printf taken as that first argument, the 0th argument? String. So I'm reading this all as a string. The percent is 1 character, 9 is 1 character, 4 is 1 character, and the C is also 1 character. So there they go, they're right there. What comes next? A percent character, a C character, percent character, C character. That's 4 characters in total, fills up that row. Then I have a percent and an N, that's 2 characters, fills up part of that row. And all of this fits inside buffer, it's less than 28 characters. So that's my input. And that's what it looks like on the stack. Okay. Anything on Zoom that people want to know? There was a question, does printf always assume its arguments are 4 bytes? For today, yes. But sometimes maybe not. Question?
So the way this is written on the stack, is FCAT reads 28 characters, you need to start overwriting. This buffer is only 16 long, so you just start overwriting this.
Oh, there's a question about fgetS takes in 28, but buffer is only 16. How about we pretend that's a 16 for today? And let's keep going. I told you there might be some mistakes. So at least for today, we're not going to write outside of buffer. I guess you technically could because I made a typo. But in that case, the buffer overflow would be the one we saw from last time. But today, I really want to do format string vulnerabilities. So we're going to try to get this done writing inside buffer. Okay, you caught me. I'll fix that later. Okay, good catch though. Okay, so this is one possible way to interpret this input, is to count the number of bytes that it takes up in memory. That's what I've done here. And I've used the number of bytes it takes up in memory to fill up the stack. But that's not the only way that this could be read. In fact, there's somebody who reads this input differently. You know who? Printf. Printf reads this input differently. How does printf read it? Printf goes character by character, byte by byte, and every time it sees a percent, it's like, okay, time to go on the stack and grab another argument and read it. So you can almost think of it as like printf is like making friends. It's like matching up buddies. Every time it sees a percent formatter, it goes on the stack and it chooses the next argument to be friends with the percent formatter that it sees. So every percent formatter should have a friend. It should be paired up with somebody on the stack. So if I have 4% formatters, then I need to go pair up 4 arguments on the stack to be friends with those 4% formatters. They might not be actual arguments to printf if they're mismatched, but still 4 things on the stack have to match. So let's go match them. So printf goes character by character. EF, that's the byte, you're not a percent. BE, you're not a percent. AD, not a percent. DE, not a percent. So for those first 4, no friends were made. There were no percents, so we didn't have to go on the stack and match the percent with an argument. What comes next? Aha, percent. So what does the printf function do? It goes on the stack, takes the next thing that has not been paired up yet, and it says, all right, well, the next thing we haven't paired up yet is this arg1. So now you are friends with this percent formatter. Anytime I see this percent formatter, I go to its buddy on the stack read it somehow, and then read or write something interesting. What comes next? %C, another percent. Well, you haven't made a friend yet, so let's go on the stack, find the next thing that hasn't been used yet, happens to be arg2. Now you're friends with that %C. Anytime I see this %C, I go on the stack, get arg2, or whatever's at that arg2 address, and something interesting happens, hopefully, a read or a write. Another %C, you get the story. This one matches up with arg3, and then the %n, that weird %n that we care about, that matches up with arg4 right there. So that last %n, sorry for all the crisscrossing lines. Critical thing is that this %n, it matches up with the arg4 thing on the stack. And what a coincidence. I've done a good job juggling because that %n, it just so happens to match with that deadbeef. If this input were even a little bit different, that might not be true. But I've really carefully configured this input so that when that %n occurs, the next thing on the stack, it just so happens it's the address I want to write to. So %n makes buddies with that deadbeef address, which means when that %n occurs, what's printf going to think? It's going to say, time to go on the stack, get %n's buddy, go to that address and write something. And it just so happens, thanks to the way that I set up this problem, that that %n goes on the stack, finds deadbeef. It's not immediately obvious how you would line these things up, but in this case, that's how they're lined up. There was a question about %C. I promise I'll get to that in like one slide. There was a question about how do I know the character length of elements? In general, you don't for a %s, but we're using %C. Okay. So I'll repeat that one more time. The question was, if you're doing %s in a string, how do you know how many characters get printed out of the string? In general, you don't, but here we're using %Cs, so we don't have to worry about that. And we'll talk about the %Cs in one slide, so don't you worry. Okay. So that's one way that the printf reads my input. It looks for all the %s, makes buddies with things in the stack. Anytime I see a %, I go to the matching thing on the stack and use it to read or write something interesting. But that is actually not the only way that the printf function reads things. Remember, there's one more way that printf reads or interprets the input and output, and that is the number of bytes printed. You thought juggling 2 things was hard. Let's juggle 3. This is the last thing that printf thinks about, which is how many bytes have been printed so far. So at the same time that printf is thinking about all those % and the % making friends with things in the stack, it also has to keep track of how many things have I printed so far. So if I ever see a %n, I know what to write. So printf is keeping track of 2 different things at the same time, which means that you, the attacker on project 1, you're going to think of 2 things at the same time as well. You're going to think of every single time I see the %, what am I matching with on the stack? You are also going to think about whenever I'm using printf, how many characters have been printed so far. So let's go through and think about printf again and think about what printf is thinking when it's looking through and thinking how many characters have been printed. I said the word think a lot there, sorry. Okay, so here we go. The byte EF that gets printed prints 1 character, another character, another character, another character. In total, 4 characters have been printed. What comes next? This weird thing. I haven't told you what this does yet, but now I'm going to tell you. That %C, it prints out, it goes on the stack, takes the next thing and prints a character. Except I have shoved a strange number in between. That strange number is weird. Again, this is printf trivia, but really useful for attacks. That number in between tells me print out the character, but pad it using spaces until it's 94 long. Okay, so I'll go on the stack, get a character, and I will pad it with spaces until it's 94 characters long. So I'm probably going to print 93 spaces followed by a character. Why does printf do that? I don't know, printf trivia. But in this case, turns out to be pretty useful for my purposes because if I do that, 94 characters get printed just by using this little input. So this input did 2 things. It went on the stack and used up one of the arguments so that future % use arguments even higher up. And it also costs 94 characters to spill out into whatever output printf is writing to or printing to. Okay. There were questions about, does this work if you do other things like 50C, 25C? You certainly could. So if you do 50C, 25C, 25C, just add them all up or something, maybe, but then you'd have to juggle all the characters and make sure that everything matches. So possible. Okay, but let's keep going. %C, what does the %C do? The %C goes on the stack, takes the next thing, reads it like a character, prints it. A character is 1 byte long, so that prints out 1 byte. But it did two things at once. This printf is doing two things at once. It used up arg2 on the stack, %c. You are friends with this thing on the stack, whatever that is. So I'm going to go there, use that thing, read it, treat it like a character, print it out. Characters are 1 byte long, so a single byte got printed. Same thing for this one. I used up this argument on the stack, and I print out 1 character. Okay. Question. What happens if you go farther up? There are all sorts of ways that you can juggle this incorrectly and strange things happen, but let's focus on the correct way to juggle, and then I can try and take some questions. Okay. And then here comes the most interesting part, which is the %n occurs. So what happens now? I go on the stack, I take the next thing that hasn't been used, and so far I've used up 3% formatters. The 94C made friends with arg1. The 2%Cs made friends with arg2 and arg3. So who's the next thing on the stack that hasn't made a friend yet? Why, it's arg4. So what am I going to do? I'm going to take that value, go to that address, because %n expects an address. I'm going to go to deadbeef, and I'm going to write the number of bytes printed so far. What's the number of bytes printed so far? By some juggling coincidence, it is 4 plus 94 plus 1 plus 1, 100. So this %n is going to go to the deadbeef address, write the number 100. %n's don't print anything. That's why I put a 0 there. But I've achieved my goal. I've written the number 100. All right, let's start to take questions. This, by the way, is not at all obvious. It's not obvious how I juggled this. It's not obvious immediately how this all plays together. It takes a couple of reads through it, but this is on your project. So that's why we're trying to go through it in a lot of detail now. And it's like a reference for you to come back to later. Okay, questions? The question about this 94, what is that? Oh, what is it writing? Yeah, gotcha. That's a good question. I think the % writes it as, I think it writes it as unsigned. Well, it writes it as ones and zeros, right? So I think it's unsigned, but I guess I can check later. Okay, question?
So characters, %c should read a character. Characters are supposed to be modified. When characters are pushed on the stack, they still scale up 4 bytes.
Yeah, that's a good question. And it's another one of those C compilers do weird things and we have to make an assumption question. So the question was, characters are 1 byte. So when I see this %c and I go on the stack, how come I'm taking a 4 byte value? So at least in this class, we're going to assume that compilers, when they push a character argument on the stack, they push the character and they push 3 bytes of padding, just so everything's lined up in multiples of 4. If your compiler worked differently, then who knows? You might have different behavior. But for this class, that's what we'll assume. It's a good question, though. Anything else? The 94 basically says, you can think of it as whatever the heck this is, it's printing out 94 characters no matter what. What it's actually doing is it's printing out a character and then adding spaces until the total length is 94. But you can think of it as somehow it's just spitting out 94 bytes. What those bytes are not important to us. We just care that we've juggled the total number of bytes to equal to 100. There were questions about, could I modify this to make it work? Well, sure. One thing you could do is someone suggested, well, hey, what if I put the number 50 here and then I put the number, 25 here. So this is %25C, right? Or I guess I can do, I don't know, let's do %50C. Okay. And then I do what's 50 plus 44 is 94C, something like that. 45, I don't know. You could certainly try to juggle this. But what you'll notice is that, okay, you're like, I can just change this and it's the same. But now the total number of characters you've used, this is still 4, but that is now 4. So things are starting to go out of whack. So that's the really tricky thing, is even a small little change could break something else. Okay. If that didn't make too much sense, don't worry. It was a specific question, but still interesting to notice how all these things have to line up together. Okay. There was a question about if the argument is not a char star, but a char array. I believe it still gets passed by reference, like an address, because that's how C strings work. They're always addresses of strings. Yeah. I'll go in the back and then one more. So you want me to put more things after the %n or before? Sure, we can stick something here. Oops. I will stick, what do you want to stick? %c after here? Sure. So that's going to take up 2 more spaces on the stack. It's going to show up right there. What's it going to do? It's going to consume another argument. So now it's going to consume arg5. All right. what's really weird here is that the printf is starting to consume its own input, which is kind of weird, but don't worry about it too much. It happens. What does %c do? It prints out 1 byte. So what's it going to do? It's going to go to this address, take a character here. How the characters are organized are kind of beyond the scope of this particular lecture, but say it's the least significant byte or whatever, the %, and it prints out the %. So if I did this, I'd get an extra % character afterwards. But yeah, pretty weird. Don't worry about it too much. You'll get practice with it. This is definitely one of those things that comes with practice. And even once you do have it, getting all these things to line up perfectly is pretty tricky. So yeah, sorry, I forgot. One more question.
For just for like trying to rearrange like 94, like 45,
Mhm.
and so the number of characters change. Is there any problem in this case?
Yeah, there's a question, which is what happens if the number of characters changes? So suppose I do, and this is a good example of, this is the stuff you'll be struggling with on project 1. Right? It is tricky, right? Because when you change something, sometimes other stuff starts to change as well. And that's what I mean by you have to get all the stuff right at the same time. And that's what makes these questions so tricky. You're like, I just want to change that 94 plus 1 to 45 plus 50. Aren't those the same thing? But remember, these are bytes that I'm writing into memory. Before I wrote %94C %C. That was 6 characters in total. Now I'm writing %45C %50C. Now I'm writing 8 bytes in total instead of 4. So what that means is on the stack, when I try to draw this out, suddenly here, instead of writing %C, I actually wrote %50C. And then one of those %Cs got bumped up here, right? So does that change anything here? I guess in this case, you lucked out and it didn't change anything, but who knows, right? The more you change these around, things could change. Maybe you like run out of space in buffer, or maybe that dead beef gets moved up or down. So it's really tricky to get these in the right place. I guess in this case, you lucked out. This might also work, but in general, and all bets are off. Okay. The question about the 28, the answer to the 28 is it is a typo, which is a 16. So that's just a way for us to exclude the classic buffer overflow where I just overwrite the RIP because we want to talk about printf vulnerabilities. So the fgetS is just a way to stop us from writing out of bounds, except I did it wrong. So I guess technically you could write out of bounds. But in this question, we're trying to not write out of bounds ourselves, but let the printf write out of bounds for us. Okay. There was a question about, is it 44 or 45? I think it's 45 because 94 plus 1 is 95. 45 plus 50 is 95. So they add up to the same thing. Total number of bytes printed. Okay, I'll take one more question and then I'll show you another project 1 exploit that's a little bit easier. Okay. Yeah, there was a question about why did I put string here? I am not going to lie to you. Lining this up took me a long time last spring. And those string characters were the only way I could think of to make things line up and actually have things fit on the slide. So that's my honest answer. Why is the string there? It's because I couldn't get things to line up without it. You'll also get to experience this in your project 1s, but I promise in your project, there is a way to line things up. It's hard to find, but it's there. Okay, sorry, I don't want to scare you too much. If you do a bit of GDB and draw out these diagrams the same way we have, you'll have an okay time on project 1. Okay, there are more slides in here. So one thing you could consider before you start project 1, just to make sure you've got this down, is you could think about how would I modify this exploit if my challenge changed? So suppose I wanted to write a different number of bytes, or I wanted to change the address that I'm writing to. Which parts of this would I change? It's like food for thought after you go home if you want. Okay, now the way to stop this, I will briefly mention how printf vulnerabilities get stopped, or how you would use printf correctly. The key idea that made all of this terror possible is that you were giving the attacker control over the 0th argument. That was the key. This is the only argument that printf looks at to read those special % symbols. All the other ones after the 0th one, those are just arguments that get plugged into the %s. The only one where the % actually matters is that 0th argument. So what you have to make sure as a programmer is that 0th argument, never give the attacker control. It's so tempting coming from other languages or just not thinking too hard. It's so tempting to be like, I want to print buff, printf buff. But as soon as you do that, you've given the attacker an input or a place to go into your code and make printf do all sorts of wild things. So you have to be really careful anytime you're using printf Right? It's not just like a functionality thing, or I don't want the compiler to yell at me. We really have to make sure for security that first argument, that percent formatter, it's something we specify. Now it's a hard coded %s. If the attacker can't change our code, then they can't touch that %s. Okay. All right, that's the end of format strings. If you have other questions, feel free to come talk afterwards. This is definitely tricky. I don't expect you to understand or to be like, of course, on your first run through of it. As you do the project, you'll get more practice with it. Again, this is here because this, without any prep on the project, like terrified people. So we tried to give you a taste of it before you attempt it on your own projects. Okay. All right, so I'm going to skip over a couple slides in the interest of time. I'll come back later. We're probably not going to test you too heavily on them anyway, so don't worry too much about them, but they are here if you're interested. This is another way that you can override things on the heap. It involves fancy things like double pointers if you're interested, but we won't test you on them too hard. I'll leave them here for context if you want them, but I'm going to attempt to skip to the off by one exploit, another project one classic. This is another one that's on project one. Sometimes people see it and they're kind of intimidated by how it even works. Again, it's a pretty specific exploit, so it's not something that you're going to see all the time in the real world. But because it's on project one, because people always ask us questions about it, here is your lecture on how off by one exploits work. Okay, so you don't have to go out in the real world thinking like, oh, I really have to know exactly how this works. But for the purposes of project one, you do, at least for a little bit. So here's your introduction to it. Okay, this one I think is pretty cool because I'm going to narrow the attacker's power even further. This might be the least power that the attacker has, and still they're able to redirect execution to shellcode. So what do I mean by that? Well, let's take a look at this code. So this code, well, I can draw the stack diagram like I always do. So I write the main function. Yes, I'm technically kind of cheating by saying RIP of main, because main is really called by the operating system. Someone always calls me out on that. Let's just pretend that main works like any other function, and someone else is calling main, like the operating system, and the return value, the SFP, those get, or the return address, the SFP, those get pushed on the stack. But yes, technically you're right. Main is called by the operating system, so things are a little weird out there. Anyway, we call main. Main has no local variable, so we don't add any. The stack frame is just those two things. And then we call vulnerable. What do we do when we call vulnerable? Well, we create a new stack frame for it. And just like always, we put RIP vulnerable, SFP vulnerable. Kind of get used to it the more you do it. That's what happens when we start a function. Void takes no arguments, so there we go. And then void has a single local variable, which is name, and it's 20 bytes long. So here it is. That's name. It's 20 bytes long, so I fill it up in 5 rows. You don't have to in your diagrams, but that's what I've chosen to do. Okay. You can also suppose that I've gone into GDB or my debugger, and I've learned somehow that these are the addresses of each of the things on the stack. And you can do that in your project ones too. You can go in GDB, the debugger, you can print out all the addresses of things on the stack, and you too can draw a nice little stack diagram like this that tells you what values are on the stack and also where are they in memory. So for example, well, where is, or what's that, address CD4C in memory? Well, it's some part of that name character array. Okay. Now let's look at the vulnerability. The vulnerability comes from this place, this fread function where the attacker can read, or we read the attacker's input and write it into memory. Our name character array, 20 bytes long. How many characters are we letting the attacker write? 21. That's what fread says. So don't worry about the syntax too much, but this fread function lets the attacker write 21 things. So what can the attacker overwrite? A single byte. And you're like, there's no way that an attacker writing a single byte can execute shellcode, right? Yes, they can. So let's do it. Okay. So first we figure out, and this is another strategy that I use when I'm faced with one of these hard-looking memory safety exploit problems. The first thing I ask myself is, if I'm the attacker, what am I able to do? Because that might give me a hint of what's possible or where I should look for my exploit. And just as importantly, when I figure out what the attacker can do, I'm also figuring out what the attacker cannot do. And if I can figure out what the attacker cannot do, that can rule out a lot of stuff that might have been on my mind about possible exploits. But once I rule it out, I realize the attacker can't change those values. Then I can rule out some exploits that I don't have to think about because I know they're not possible. So the attacker starts at name, that's what fread says, and writes 21 bytes. So here's 4 bytes, 8 bytes, 12 bytes, 16 bytes, 20 bytes. they can write those. And then 21, they can write one of those 4 bytes. That's it. They can't write anything else. Here it is in colors. Okay, don't worry too much about the endianness, the left and right. That's the key of this exploit. The important thing is I can write 21 bytes and nothing else. So anything in yellow, the attacker can modify. And crucially, anything outside of that highlighted area, the attacker cannot touch. So say you want to do the good old classic buffer overflow from last time where I just overwrite the RIP and the program jumps somewhere funny. Can't do that. I can't modify this value. I can only modify 1 byte outside of the name character array. So by highlighting this, I realized this is all I can modify. The name character array, I can put whatever I want in there, and I get 1 extra byte. What is that 1 extra byte? That 1 extra byte is part of the SFP. What's the SFP? The SFP is the value of the old stack frame pointer, which tells me what the top of the previous stack frame was. Okay. The question was, what is limiting me to only the highlighted portion? Well, that's because the code that was given to me only lets me write 21 bytes. So whatever code I'm exploiting, if I can only write 21, I've got to deal with it, come up with the exploit. So there it is. That's the one and only byte I can change. Because the program is little endian, the one and only byte I can change is the least significant bytes, the lowest byte of that address. So what goes in the SFP? Like, what's the value of the SFP? It's an address. It could be a character, it could be a string, or not a string, but it could be like a number, integer, but it happens to be an address. And the least significant byte of the address, that happens to be something you can touch, so you can change it. And if you change that value, that's 60, you're changing the address that the SFP is referencing. All right, so let's do it. We can only change that 1 byte, so let's go for it. We changed it. It used to be 66. Using my exploit where I can write 1 byte out of bounds, I changed it to say 44 instead of 60. So what did that do? Well, this 60, BFFFFF60, that used to be, I guess that should be a CD, another typo. So someone tell me to fix that later. Okay, that address that ends in 60, we'll say it's a reference to this thing up here, even though I typoed one of the characters. Sorry about that. And that's what the arrow shows as well. It's a pointer or a character or a pointer or a reference or the address of that thing up there. But I am about to change it. I changed that 60 to a 44 in memory, and suddenly this is no longer a reminder to myself that there was something up here that I cared about. Suddenly, now it's pointing down here. It's the address of name. Okay. So what does that do? Well, let's think about this SFP a little bit more. So let's suppose we're back here in regular program execution. Nothing evil has happened yet. The attacker hasn't touched anything. In normal program execution, where's the SFP referencing? Well, sometimes it's not totally obvious. We might have to go back to lecture 2 and remember, but I'll tell you one useful trick, which you can kind of see up here as well. The value of the SFP, it just so happens, and if you don't believe me, go back to the lecture 2 where we talked about the stack frames and how functions get called. But it turns out there's a nice little shortcut, which is where does the SFP point? It basically always points at the SFP of the previous stack frame. Nice little side effect of the way that we set up the stack. So that value in the SFP, if you go to that address, you will find the SFP of the previous stack frame. It's almost like a chain of SFPs. For every address that I follow, I get the SFP of the previous stack frame, the SFP of the previous stack frame. That's just the way that the stack is set up. And again, you don't have to believe me. If you go back to lecture 2 and try calling some functions, you'll see that this is always the case, assuming the attacker doesn't change the thing. So if I were to walk up to this program halfway running, and I was like, hey, C program, can you answer a question for me real quick? Where's the SFP of the previous function? The C program would probably look at you really confused because it's a program. But if that C program could talk, it would say, oh, okay, well, if you want the SFP of the previous function, well, I know that the current SFP is always a reference to where the previous SFP is. So if I want to know where the previous SFP is, I can just look at the current SFP. It's a reference or the address of where the previous SFP is. Okay, that was a long-winded way to say this is what the C program thinks is here. Now I have gone in as the attacker and I've changed it. The C program was not expecting this. The C program thinks that in normal execution, this thing should not change. But we did it, we changed it. So now if I walk up to this broken C program where the stack is all messed up, and I ask the same question, which is, hey, where's the SFP of the previous stack frame? Like, where should I go to find the SFP value of the previous stack frame? What's it going to say? It's going to say, oh, just look at the value here and go there. That's your SFP of the previous stack frame. Well, no, it's not. It's not because we changed it, but now the C program thinks that the SFP of the previous stack frame lives down here. So that value that used to say SFP of main, if I now ask the program to go find it, the program would look down here to find it because I changed that one byte. So all of this is to say, by changing that one byte, suddenly now it's looking down here for the SFP of main. Okay, that was the answer to whatever that says. Okay, but there's something even more important, which is like, wait a minute, the SFP, that's not what I use to get shellcode to execute. What I really care about is the RIP. That's the good stuff. That's what I use to get the shellcode to execute, because that's how I get the program to jump to other places that I care about and start executing instructions. So again, I walk up to this normal looking C program. It probably cannot talk, but if it could talk and I asked it, hey, where is the RIP of the previous stack frame? So if I'm currently in the stack frame of vulnerable and my previous stack frame was main, and I want to know, hey, if I want to know what the RIP of the previous stack frame is, what address in memory should I go to? Like, where should I go find it? And if the C program could talk, it would say, well, this is the current SFP value. Go follow this pointer, follow this address, and you will find the SFP of the previous stack frame. And what's always above the SFP is the RIP. So if you go there and then go 4 bytes up, you're going to find the RIP. That's what this program would say if it could talk, which it probably can't. Then we come back here and we ask the program again the same question. The program does not think anything changed because the program was not expecting an attacker to go in and modify memory. So if I ask the program the question, it's going to answer the exact same thing, which is, okay, well, if you want to know the RIP of the previous stack frame, all I have to do is look at the SFP of the current stack frame. That's an address. If I follow that address, I will find the SFP of the previous stack frame, because that's what SFPs always point at. They always point at the SFP of the previous stack frame. And hey, if you want the RIP of the previous stack frame, just look 4 bytes above. So if you want the RIP of the previous stack frame, just look right there. That's the RIP of your previous stack frame. We've confused the program. It's giving us this wrong answer instead of the right answer. Okay, what can we do with that? Well, suddenly, as a result of changing this last byte, we have fooled the program into thinking that there's an RIP living here. Is there actually an RIP there? No, that's part of the name character array. But because we've changed one byte of the program, suddenly the C program gets really confused and is starting to think that SFPs and RIPs live down here when they really don't. So that's kind of the key of this exploit. By changing that one byte, now the program thinks that the SFP is here and it thinks the RIP is 4 above, which is right there. All right. So suddenly, because I've confused the C program a lot, now I know where to put my address of shellcode. Where should I put my address of shellcode? I should put it where the program thinks the RIP is. So I've done 2 things. I've confused the program by making the program think there's an RIP halfway through main or 4 bytes above the start of main. And then where the program thinks the RIP is, that's where I stick the shellcode. So I've done 2 things. I fooled the program into thinking the RIP is somewhere it's not. And then I put the address of shellcode where the program is now incorrectly looking for the RIP. So that's the way that I got this exploit to work. Now let's actually see it in action. So just like always, I've taken the x86 instructions and I've put them here. And we're going to step through them line by line to see if this does what we expect. So here we go. We're going to finish running that first function, which is vulnerable. So let's return from vulnerable. All right, here we go. So the epilogue does 3 things. It always does. The first thing it does is it takes that ESP, the bottom of the stack, and it moves it up here. The ESP is a register, holds an address, points somewhere in memory. I'm going to move it up there because by moving it up there, I've deleted the current stack frame. So moved, stack frame deleted. Okay. Next step is now I'm going to take EBP. It's a register, holds a value. Currently, it's holding the value of the top of the vulnerable stack frame. I want it to hold the top of the address, or the address of the top of the previous stack frame, top of the main stack frame. So what do? Well, I know that the previous EBP's value was saved on the stack. That's what I did. I saved my work so that I can always take the saved thing on the stack, put it back in my register. So that's what I'll do. I'll take the saved value on my stack, which happens to be this value. I'll take the saved value, put it back in my register. What happens if I put this back in my register EBP? Well, Now my EBP points down here because I took this value and I put it back in EBP. So now EBP thinks the previous stack frame top is here. Okay, kind of weird, but that's what happened. So here, EBP, top of the vulnerable stack frame, right? And I'm ready to return. So I want to get the top of the previous stack frame, put it in EBP. How do I know the top of the previous stack frame? I wrote it down on the stack when I was preparing to call this function. So I can take the value that I wrote down to remember from before, put it back in EBP. And as soon as I put this value back in EBP, now that's the value in EBP. EBP now has that value ending in 44, which is equivalent to saying it's pointing at that address 44. That looks kind of strange, but let's keep going. The final thing we do is EIP, the instruction pointer, is ready to go back to what it used to be. Currently, the instruction pointer holds something in vulnerable. It's pointing at some instruction in vulnerable, but I want it to go back to where it used to be. How do I do that? I take the next thing on the stack, which I put on the stack earlier to remind myself what was in EIP, and now I put it back in EIP. And here's the important thing. I did not change this value. Like, look at it. It's great. I didn't change it at all. So when I put this EIP back in, or when I put this RIP back in the EIP value, shellcode's not going to execute. Nothing interesting is going to happen. I'm just going to go back to the main function because this is not changed at all. So it's not like those classic buffer overflows where I change this value and I jump somewhere where I have shellcode. This is unchanged. So when I shove it back in the EIP, I just go back to main like I always do, as if nothing happened. So look, I'm back in main. Okay. See that EIP? It went from vulnerable and it went back into main. Okay. So that was the vulnerable function returning. And you're like, wait a minute, you're not executing shellcode. Like, look at the instruction pointer. The instruction pointer, that's not shellcode. The shellcode's at deadbeef. So, my first function return actually did not get shellcode to execute, but that's okay because I have two functions. So that's the other key of the off by one exploit, is that it does not just take one function return for things to happen. It takes two function returns for things to happen. All right. But after the first function return, things are starting to look a little strange. So if we look at the stack, well, remember, the ESP points to the bottom of the stack. So if I ask the program, where's the bottom of the current stack frame? Well, the bottom of the current stack frame is, well, it's right there. That's where ESP is. Where's the top of the current stack frame? That's wherever EBP is. So where's the top of the current stack frame? Right there. Okay, so somehow the bottom is up here, top is down here. I told you, things are starting to get weird. Okay, but the program can still continue. All the registers have values. We can continue on and try to return from the second function with only one difference. So the only difference is that this value down here, it should have been up here. It should have been pointing to the top of the main stack frame. EBP should have been up here. Why did it change? Because I changed its saved value and I changed one of those bytes. So when I put that saved value back in EBP, now it's in the wrong place. So that's another way to think of the off by one exploit, is to say all the way back here. Sorry to keep rewinding. All the way back here, I only changed one thing, which is I changed that 60 to a 44. That's the one thing that I changed. And what does that value represent? That value represents, after the function returns, what goes in EBP. So if I change only one value, and that value is what goes in EBP, then when I return from the function, what's different? The thing in EBP, that's the one thing that I changed. So as I expect, when I return from the function, everything is normal. I'm still in main. My stack frames are still set up the way they were. Everything went back to the way it was, except for one thing, which was the thing that I changed. I changed the old value of EBP. So when I restore that old value of EBP, now EBP's value is incorrect. It's pointing down here. That's not the top of the stack frame, but the program thinks it is. Problem. Okay. Now let's try to trigger the second function return. So time for the second function to return. We follow the same 3 steps we always do. All the functions end in the same 3 steps. So what do? I want to first delete the stack space. So I take that ESP and I move it up to the EBP. That's not up, that's down. That's because the stack is all messed up, right? So normally in regular function execution, the way that you clear stack space is you move this thing up, but because the EBP is all the way down here, I'm actually moving it up in quotes. Okay. So now it's here. That's the first step of any function return. What comes next? Well, what comes next is I take the next value on the stack which is always going to be the SFP at this point. If you don't believe me, lecture 2 will convince you, right? The next thing on the stack is always the SFP. That's the value that needs to go back in EBP when the function returns. So I take that value, I put it back in EBP. What's that value? It's some A's. Okay, those are some bytes. I can put those bytes in the EBP register. And what's EBP going to do? It's going to fly off into nothingness, just like we saw from last time. So that EBP register, it still contains a value, A. What is that the address of? I don't know. It's sitting somewhere up there. All right, SFP is gone. So we used up the SFP, we put it back in the EBP register for the main function. And now the final step of main is to return. So what happens when you return? You take the next thing on the stack, which is always going to be the RIP. It's the RIP. It's a fake RIP, but still it's the RIP, or the program thinks it's an RIP. So we take that next thing on the stack, we put that in EIP. In other words, we go to that address and start executing instructions. So at long last, it took 2 function returns, but I'm starting to execute shellcode. Okay, there it goes. So that EIP, it used to point here. I took that value on the stack, I put it inside the EIP register, and now the EIP register is pointing at deadbeef where I put my glorious shellcode. Okay, this is another exploit that you have to do on project 1, and it's another exploit that just by watching me talk through it, you're probably not going to get all the intricate details that go into it, and that's totally okay. This lecture is not like you have to memorize all of the steps. It's more like a way to get you familiar with these so that when you go into project 1 and you're coding up the off by 1 in question 4 and the vulnerability in question 6, you're hopefully not like totally terrified. Okay, can I take some questions on this? Okay, because I'm sure there are some. Yeah. Yeah, there's a really good question, which is how would this even happen in real life? So you're right. We kind of came up with something a little bit convoluted here. Wait, can everyone? Shh, I'm gonna take some questions and then you can all go home. Okay, so yeah, here we kind of did a convoluted example where I just gave you 21 bytes for no reason. But you can imagine that in real life, off by 1 errors happen all the time. Sometimes people read the function wrong, or they think that fgetS needs to be 1 more. The argument to fgetS has to be 1 more than it is. So it can happen in real life. The example here is a little bit contrived. The example in the project, I think, is a little bit more realistic, but off by 1 errors, they can happen. Okay, everyone is so impatient. So here's what I'll do. You can all go home, but if you have questions, I will stay here. So I'll be here. You go home and I'll see you on Monday. Okay, bye. There was a question about why it doesn't go to deadbeef on the first return from Zoom. So the question was, how come it doesn't go to deadbeef on the first return? There's a lot of ways to answer that, to be honest with you. And the more you walk through this, the more you'll see different ways to answer it. But to me, the most obvious answer for why it doesn't return to deadbeef on the first return is because on the first return, how does the function know, the function vulnerable, know where to go back to? It looks at the RIP. That value on the stack, the RIP of vulnerable, this is where vulnerable is going to go execute instructions after it returns. And we didn't modify it. So because we didn't modify it, when the vulnerable function returns, we go back to where we were, or where vulnerable came from, which was main. So we did not overwrite the RIP of vulnerable. To me, that's the clearest explanation for why it doesn't return the deadbeef on the first try. But there's lots of other explanations you can come up with based on this exploit. There was one more Zoom question, then I'll take the real ones. So, or the real in-person people. How does ESP get moved up when we pop EBP? Remember, the pop instruction, this is straight from lecture 2. The pop instruction, what it says is take the next thing on the stack, put it in the EBP register, and because I've used up that thing on the stack, move ESP up by 4. So the reason why ESP goes up when I call pop EBP is because the pop instruction says take the next thing on the stack and then move the ESP up by 4 because I just used up that thing on the stack. So it's like a lecture 2 trigger. Okay, those are all the Zoom questions. However, I will keep the Zoom open and I will start taking questions in person, but I will stop the recording since it's around 6:30. So for people watching at home, I'll see you on Monday.